Okay, welcome back, guys. So before we get into the main content that's in the title of today's lecture, I want to start with a little mathematical aside. So this is a math fact, which some of you may or may not have known. But here we go, let's get into it. So I'm going to draw a coordinate axis here. And on that axis, I'm going to put the sine function. Now I hope you guys are all familiar with the sine function. It looks something like this, and the equation that defines it is y of x equals sine of x. So of course this is the x-axis and this is the y-axis, all right? And the sine function. Now, the mathematical fact that I want to real quick discuss is that if I graph y of x equals x, just plain old y equals x, that's a straight line. I want to make sure I draw it right for a specific reason. That's a straight line and it looks like this. It goes through the origin. So the thing I want you to notice is that in this general area right here, y of x equals x and y of x equals sine x, they kind of overlap. They're very, very, very close to each other, all right? Now it's really important to notice that as you keep going, as x gets bigger and bigger, right? Because this direction is increasing x. There's an arrow here. X gets bigger, then sine of x deviates from it. So if my x is way out here and I want to know what y is, I'm not going way up here to this line. I'm actually coming down to the sine function. But right here, near the origin, for small x, sine of x is almost the same as x. And I'm going to use this little squiggly to indicate that it's not quite equal, because that curve and that line, they never quite are exactly equal. But they're so close here that they're within the width of my marker, okay? It looks like that's lying right on top of that. So if my x is small, those two functions are the same. And this is something that's useful to know if you continue in physics. Physicists use this all the time, but it only works when x is small, and that's why, all right? So with that mathematical aside out of the way, let's start today's lecture. So I want to talk about something called an equation of state. So this is a really fundamental topic in thermodynamics, and to get into trying to define it, the first thing we have to see is that it has the word state in it. So I want to refresh your memory with what a state is. So a state is a collection. Remember, it's a collection of state properties. All right, we discussed what a property is. And so, for instance, pressure, temperature, and specific volume are such properties that I might include in my state, in my collection. Now, I used specific volume here, and I've been drilling home about specific volume a lot recently in our Zoom meetings. The reason why I didn't use regular volume is because I want all these to be intrinsic. Remember that regular volume is extrinsic, whereas like pressure, temperature, and specific volume, those are all intrinsic. And so I really like intrinsic things. They're nice to work with in physics. And so when I build my state, I want my collection to be of intrinsic variables. And that's why I use specific volume instead of regular volume. So that's what a state is. Now, what is an equation of state? Well, here's how I think of equations of state. This is a math machine, all right? And this math machine takes in these variables: pressure, temperature, and specific volume. Now, I'm not saying that it takes in any three variables. This is not general. It takes in these three specifically: pressure, temperature, specific volume, only those. It takes them into this machine and it combines them. And you can combine these three in any way. So your mathematical operations, your ultimate goal is to get an equal sign out the end, all right? So first you can do your plus, minus, divide, multiply. You can do exponents, logs, you can raise to powers, you can do any functions, you can do square roots, and you can multiply by numbers, right? So if I have the pressure, I could also have twice the pressure. So I could put a random number in front, okay? So I can do all these mathematical operations to these three things, mush them, mash them together in any way I want, and it's gonna spit out an equation, all right? And this equation that it spits out is an equation of state. It's one of an infinite number. This is the important point that I want to make, is that this, you can easily see, has an infinite number of ways to do, all right? I can put these three in and use mathematical operations in an infinite number of different ways. So if I was going to list all the equations of state, this would be an infinite list. It's literally anything on this list is anything I can do into that math machine and spitting out an equation at the end. So I want to write down just a few, just to show you what's possible. I could do, and I'm going to use my cheat sheet because I don't have all these memorized. I could do a number times temperature over the volume minus a number. Okay? I could do volume pressure times volume minus number equals some number times temperature times exponential, bring in an exponential into it, over temperature times specific volume. Okay, so this is one, and these have names. So this one right here is the van der Waals equation. This right here is the Dirichlet equation. And there are tons more, an infinite number. So you may be wondering where I got these. I'll explain that briefly, but basically they're valid. All you need to care about right now is that they're on the list. They're valid because there's some weird permutation of things. This list, I'm going to draw a big ellipsis. This list goes on forever. They don't all have special names, but this list goes on forever because I can combine those things in any way. All right? Now, if I wanted to say, well, that looks really complicated. Those look complicated, and I don't know where I got them. So let's scrap that and start from ground zero. You want me to build an equation of state. What is the simplest possible way I could do that? Let me think of something really, really simple. And historically, this is what people did. And there's Charles, there's Boyles, and there's Gay-Lussac. Lots of guys who, throughout history, sat down and started and said, let's start with simple equations. And here's what they came up with. Look how simple it is. One equation on this list is P times V equals temperature. Now, this is super simple. They called it ideal. This is an ideal equation, all right? These are they're pretty complicated. They're not ideal. This is ideal. And so the name of this is the ideal gas equation, or the ideal equation of state. So I'm going to write that. So I could call it just the ideal equation. I could call it the equation of state, the EOS. I could call it the ideal, I'd call it the gas law, ideal gas law. That's the same thing because it's about how gases operate. And I could call it the ideal gas relation. All these are the same names for the same thing, okay? The point is that this is an equation which is ideal. Now, I made one caveat to this. What if the pressure times the volume isn't exactly the temperature? What if it's like twice the temperature or 3 times the temperature? That's allowed, right? So there could be a number here. And I'm using this for number because I'm old enough to remember when this pound sign meant number. I know it's hashtag now, all right? But anyways, so this is about as simple as it gets. You multiply the pressure and the volume, and you get a number times the temperature, all right? So this is an ideal equation. Now, the question is, with this, are there any actual real-world fluids that satisfy this? Because remember, we didn't start the way that we typically start in science, which is what does the physical world around us look like? And then how can we mathematically describe the physical world? We're going from math trying to describe real things. In this case, we were kind of backwards. We started with math. We said, take these three variables and use all of math to mush them together. And then, in the physical world, what real systems follow those equations? All right? And so, an ideal gas, the definition of an ideal gas, a gas which follows the ideal gas law. Okay, it's kind of a backwards definition. It's saying start with just pulling some mathematical thing out of thin air, make it as simple as we can, and then which gases follow that law. That's literally how it's defined. So an ideal gas would be anything that follows this law, and there are many of them, okay? Many gases follow this law. But do they follow it perfectly? No. So if a fluid follows this law perfectly, we call it an ideal gas, and it's imaginary, it's made up. There are no fluids in real life that follow this law perfectly. But there are a lot of fluids, a lot of gases, that follow it pretty well under certain circumstances. So what do I mean? That's what I did this mathematical aside for. Do you see how I could say about this system that this blue line follows this green line pretty well if I'm in this region for small x? Okay, out here, absolutely not. That blue line shoots off and this green line oscillates and they have nothing to do with each other. But if it's small, it follows it pretty well. That's how this works, the ideal gas law. If things get crazy, and by crazy I mean high pressures, high temperatures, and high volumes, then this doesn't describe the real world, all right? They blow up. This goes in one direction and the real world goes in another direction. They don't have anything to do with each other and it's pointless. But for small pressures, temperatures, and specific volumes, this works pretty well. So real is about equal to ideal, okay? So this math at the beginning, I just wanted to give you an example of what I mean when I say for small variables. When things are nice, when things are small, this does a pretty good job of describing what actually happens. These other ones on this list, I wrote down a couple that have special names because they're also guesses. They're more complicated guesses as to how things work in the real world. Again, they're not perfect. They just happen to go further. You can get a little more crazy and those work. But if you get too crazy, again, you lose those, okay? So these are all approximations of what is really going on, but the ideal gas law is a pretty dang good approximation, and so that's why we talk about it. All right? Now, for the rest of the time here, what we're going to talk about is this number. PV equals some number times the temperature. Now, I want you to just take a minute and appreciate how simple that is. That's how it got its name, ideal, from its simplicity. It's beautiful, it's easy to remember, okay? And what we're gonna do is talk about this number, and it's gonna get a little crazy. And I just wanna make sure that as it gets crazy, talking about this one number, you don't lose sight of how simple it is. It really is a simple equation. There's just a lot of stuff to remember when it comes to that number right there in front of the temperature, okay? So, in history, they said, all right, how do we write this? And the first and most obvious way to write this, let me draw a table. And my entries in the table are going to be different ways to write this number. Okay, that's what I'm going to be writing. Basically, what is this number? So the first way that they wrote it is just as a constant, and they called it R. I'll write that bigger, sorry. The letter R. So R is called the gas constant. Now, the thing about the gas constant is that it's different for every gas. So depending on whether you're talking about helium or water, vapor water or mercury or anything like this, you're going to have a different value for R. With one thing it's going to be this number, with another thing it's going to be this number. So you have to look it up in a table. That's what the plain old gas constant is. All right, it changes and it's different for every gas. So I can't write down a number for it. What number is it? I don't know. Tell me what liquid we're dealing with. So pretty quickly, people moved to this, which is another representation for that number. R universal over M. And I want to just fill out the rest of this table and make sure that I have room for everything that I need. Okay? So, people said, let's write this in terms of a universal gas constant. And that's what RU is. Universal gas constant, okay? The U means universal. Now, with the universal gas constant, I can write it as one number. The difference between gases comes from this in the bottom, which is the molar mass. Molar mass, okay? And what the molar mass is, you guys might remember from chemistry, it's the mass, like the actual value in kilograms or whatever, per mole, okay? Mass per mole. So this changes now. Instead of just an R value changing, we can get a universal R value, but we have to look up this, the molar mass, for whichever substance we're dealing with, all right? The benefit of doing it like this is because the M, you can already get off a periodic table, and RU, we can write down, right? It's a universal, it's the same for all numbers. So this is about 8.314, and it has a unit on it. The units are needed to make everything nice. It's kind of a funky unit. It's joules per mole Kelvin. Okay, remember that these are all written in terms of SI base units. Joule is a nickname, but it's in SI base units. And so this is the expression in base units, all right? And those are just the units that are needed to make the equation have all the same units throughout. So that's what the value is of the universal gas constant. So then what people realized they could do is this molar mass here can be written, remember what it was mass per mole. So this was mass per mole. Lowercase n is the number of moles. Okay, so if n is the number of moles, the molar mass is m over n, number of moles. So this is another alternative for how to write this, RU n over m. Okay, so I've replaced this m on the bottom with this, and then the n flipped up. Again, these all mean the same thing. There are different ways of writing that same number. All right. Now, with this n, let's review what a mole is. So remember, in lecture 1, we defined a mole. It's a base SI unit, and it's the unit of substance. It's used for counting things. So a common example, I used jelly beans before. I want you to think of a dozen. It's another example that's commonly used. A dozen is a nickname for a certain number of things. So a dozen is the nickname for 12 things. It's a counting number. A mole is a nickname for a certain number of things. And that number is a huge number, all right? And I'm gonna write it here in a second. But that's all that a mole is. If I start counting, I have 1, 2, 3, on and on and on, till I get to the number, which is called Avogadro's number. 1, 2, 3, on and on, Avogadro's number. That many things is a mole, okay? That's my name for that many things. And it's the base SI unit of numbers of things, okay? So, this n, number of moles, I could equally write this as the number of particles over Avogadro's number. All right, so n number of particles. This is my actual things that I'm counting, like how many actual molecules are in my system, all right? And then Na, that's Avogadro's number. It's a number, it's dimensionless. It's like 12, all right? So just like a dozen is 12, a mole is Avogadro's number. That's how that works. And this number equals about 6.022 times 10 to the 23. This is a 1 with 23 zeros behind it, okay? That's a lot of stuff, but when you're counting particles, it doesn't take a lot to get a 10 with 23 zeros behind it number of particles, all right? So, this, I hope you see, number of moles is just, this is another way of writing that. The number of particles over how many particles are in a mole. So, that gives me another representation over here. Ru N over M N A. Okay, I'm going to write that. Reasons you'll see in a second. Okay, and then I don't need this last division right here. All right, so now our expression is starting to get a little bit complicated. And you'll notice that now with this way of writing it, there are two universals. Some stuff changes depending on the system that you're talking about, and some stuff doesn't. They're universal constants. There's Ru, which is a universal, and there's Avogadro's number on the bottom, which is a universal. And so there was a fellow Boltzmann, physicist named Boltzmann, and he decided we don't need two universals, we can have one universal, and it's just going to be the ratio of them. So this whole thing right here, we can nickname KB. So this is for the Boltzmann constant, and I still have my n over m. See what I've done? I've taken Ru divided by Avogadro's number, and I've called them one thing, okay? So this I'll add to the list. This is an uppercase B for Boltzmann. This is the Boltzmann constant, okay? And all it is this divided by that. But it defines another way, yet another alternative way of writing that number. So far, I have 5 different ways that I can express this one number. And they're all the same, but they're different in the way that I write them, all right? Depending on what I'm given in the problem. But there's more. This equation right here was written with specific volume, but some people in physics, and especially in chemistry, they like to sacrifice that specific volume. And that's nice because it's intrinsic and stuff. But if you want to work with regular volume, you can. Remember that this specific volume was regular volume divided by the mass, okay, equals some number times T. Okay, I've just rewritten what the specific volume is. And what I can do is multiply the mass on both sides. So here, I multiply it, and here I multiply it, and that allows me to cancel this. So I just have P big V, P actual volume, equals the number, but now this mass is included in the number. So there's an alternative way of writing each one of these. So I can do the mass times R. The mass times the universal gas constant over the molar mass. You'll notice when we get to this one, the mass was already in the bottom. So if I do that thing and I multiply it up, that just cancels it. So now it's just universal gas constant times N. Same here, RU, N over NA, and finally, just KB times N. All right, so these are all ways of writing that number if the mass is included in that number. All right, as I multiply, it's like absorbed into the number now. So I can write it like that. And there's yet a third way of writing this value if I include something called Z. So Z is called the compressibility factor. And I'm not going to go into too much detail, but it's called compressibility factor because it has to do with the ratio of volumes. All right, so how much do the volumes compress in relative to each other? And it's a measure of how, as the volumes change, does the ideal gas law go wrong from how it really works? Remember, we talked about how the ideal gas law only works for certain systems under certain conditions, but then there's the way that things really work, and that's why the gas law is ideal. Well, this measures that. So for an ideal gas, Z is 1. Okay? So Z equals 1 is ideal. If Z is close to 1 but not equal 1, so I'm going to do a swiggle, Z is about 1, then we're pretty close. We're pretty good. Pretty good. And if Z is really, really not equal to 1, so not equal, not even close is what I'm saying, then we're pretty bad. So Z just measures how close we are to being an ideal gas. All right, how close does that equation actually measure the real properties of the gas? And for an ideal gas, since Z is 1, we don't have to write it. That's why we can just write this for an ideal gas. Okay, Z equals 1, we don't have to put it there. But we could do PV equals some number times T, and we could absorb into this constant, the Z. All right, we could stick a Z there. So that means that we have Z times all of this. So we can write all this again with Z, the compressibility factor, in front. Okay? So in closing, I just want to reiterate that even though there's a lot of ways to write this number, and it can get confusing depending on how you see it, right? If you see this equation, PV equals KVNT, that's the same thing as PV equals MRT, right? It's the same equation, and it's pretty simple. It's a simple equation. That number just has a lot of ways of being written. Okay? All right, I think that's it for this time. Thanks, guys.